Bem-vindos vocês ao canal de Astroparticles Natal. Eu, Ensino Paulo, estudante de doutorado.
I think we are already
Pela primeira vez. Primeiro, deixa o seu like.
in live. Okay, so I hope it's good to see the notes. But first, today I will talk a little bit about dark discrete gauge symmetries, and it's based on this paper from Brian Battle, and it's from 2010, but it's a good paper. It's really recent. I mean, actual, current. Basically, in this paper, he will address how we can construct models that have discrete symmetries, and these symmetries maybe could, for example, lead to multi-component dark matter, for example. So first, I will just use my notes because it's easy. So, but besides just multi-component dark matter, we could also have, for example, new light states in these models that could affect Higgs decays, and also it could affect, for example, some DM scattering in direct detections observables. So it is very interesting that we can, for example, build a model with two dark matter components, and the phenomenology of the dark matter will change a lot, include because we could have, for example, in general, we just have for a dark matter component, for a model that have just one dark matter component, usually we have that process that goes from dark matter, anti-dark matter, go into fermions, for example, via Z prime portal, or we can have also a Higgs portal or something like this, but usually the annihilation channel is very standard. But in this case, for example, we could have semi-annihilation process, because we can have how can I say it? We can have couplings with three dark matter particles, for example, and a scalar, for example, then that could interact with a Higgs. So they will call this kind of process semi-annihilation dark matter, where we can have dark matter annihilating with dark matter, but creating dark matter particles and some kind indivisible, for example. But anyway, so the idea behind these discrete symmetries, and the way that he calls gauge discrete symmetries, is that usually we start a model, for example, the standard model, and then we want extend this model, we want go beyond the standard model, and then we introduce a new abelian symmetry. That's one of the most simple extensions of the standard model. So we can choose, for example, a B minus L symmetry, where B stands for the baryonic and L stands for the leptonic number of the particle charge under this symmetry. But then you say, okay, I want a dark matter candidate in my model. So usually people use a symmetry called Z2, which is the simplest one. And in this symmetry, basically what it does a reflection in the field. So it goes from, for example, I take a field F and goes from F to minus F, for example. So this kind of symmetry will prohibit some terms in my Lagrangian that prevents my dark matter particle to decay into another particles. So we say that dark matter is stable. So at the first idea is, I want a particle that is stable, that is stable in terms of cosmological scales, and it doesn't have charge, at least. Okay, there's a lot of things that we can talk about it, but in principle, it doesn't have charge, right? So, but it's very weird, as I was talking with Álvaro, for example.
Write the final diagram for the same manipulation.
For example, usually the most usual diagram is something like this. So we have dark matter, which is my pi particle. We have a z prime. Usually it will be a neutral current, as Álvaro was talking, and we're gonna have Fermions of the standard model in the final states that we're gonna measure, and that's what we see. But in these models, we can have semi-annihilation processes. And this process is basically, for example, if I have, if my dark matter particle is a scalar, I could have something like this. But it doesn't need to be a dark a scalar. It could be another part. So let's say that's my dark matter particle, and this is my Higgs, and this is my dark matter particle again. So I can have this kind of process where I have dark matter in the initial state and the final state. But I could also, for example, suppose that I have two dark matter particles, and one of them is a fermion, and the other is this scalar. So in this case, I could have also kind of semi-annihilation process, where I would have, for example, my dark matter, my two particles, fermion interacting with, let's say, it's not good.
That's okay.
Could be something like this. We could have something like that. So we could have some. Okay, it doesn't matter. It's just avoid complexity. But we could have this kind of process. So in this case, we can see that there is an interaction. The first thing that I think that's very important to know when we are talking about dark matter and models, these things, I think is that we have to first understand that there is different sectors. We are talking about what we call dark sector. Dark sector not necessarily means that we have just dark matter particles. We could have dark scalars that are not dark matter, but will interact with dark matter because it is in the dark sector, for example. And there is the visible sector. And what we want, usually, we want to connect these two sectors to have phenomenology. But okay, so let's go ahead here. So, okay, as I was talking, I don't want to say just that I have a Z2 symmetry, what we call just a ad hoc symmetry. I'm just saying, I put by hand that there is this kind of symmetry in nature, and that doesn't explain where it comes from. So the idea is to use what Álvaro probably talked today also, what we call gauge symmetries that generate interactions in nature. So for example, the photon, the Z, the double, the gluons, all of them comes from a gauge symmetry. So the idea is, if I'm saying that there is interaction between these two sectors, I'm saying that there is a fifth force in the universe, a fifth interaction in the universe. So if I'm saying that, I will have to, I have to put this in my equations. I have to put a new symmetry. See? So because the symmetry will give me a boson, and the boson, the gauge boson, will carry this charge, and then the interaction will be possible. So if I have this setup, now maybe by math I can build a discrete symmetry, because if I broke, that's something that we'll talk in the next lectures. But sometimes we don't want a symmetry to be conserved. We want to broke it. When we broke it, it means that it is not conserved today. So like, I will just put it forward, but in the case of standard model, for example, we have SU2 left, U1 hypercharge. This is weak. The weak interactions happens here. So we will broke it to generate the masses of the particles, etc., via the Higgs, because, for example, the Higgs will have this charge, and then we generate electromagnetism. And this symmetry cannot be broken because the photon is massive, is not massive, it's massless, and blah, blah, blah. But it's another topic. But anyway, so now I want to explain, let me show here. Okay. Talk a lot. But anyway, so if I can, for example, if you see here, it's missing, it's an N, this N here. So what is chi? This is chi 1, and here the denominator is N. Because
the one that's running is
yeah.
Okay.
The point is, when we have a U1 symmetry, for example, as the Higgs said, U1 this symmetry, it is a kind of transformation that does something like that. Minus or plus in way, but it's I, the charge, then the field. Okay. But in this case, there is a charge related to this field here. When we break a symmetry, maybe there will be remanent symmetries, subgroups, subsymmetries. It's like I have a big thing, I break it, and many things go apart. So I will have pieces of this symmetry. Because it's like, okay, I have a ball, I have a sphere, for example, a sphere, and I just take a section of it. So I will have just a cycle. And the cycle has other symmetries, which is not 3D symmetries, for example, like rotation in three dimensions, etc. Okay, so it's broken. It's like I'm diminished my space of symmetries, something like this. It's related to manifold systems, but that's okay. But anyway, if I break my symmetry, at the end of the day, the particles will be assigned with a charge under this gauge symmetry. Then we have, for example, the charge of the electron is -1, the charge of the proton is +1, etc. So if at the end of the day, it's not the best example. But for example, the electron has electronic charge, but it's not a good example. But okay, that's okay. Basically, what I mean is, at the end of the day, we're gonna have particles with some charge that comes from this symmetry breaking, and we can see if we already do it, thinking the future that after this broken symmetry there will be a charge value that will respect another symmetry. Then I will have an explanation for the existence of this new symmetry that appears. Instead of being an accidental symmetry, it will be something that comes from some fundamental thing. You got it?
Okay, but so just in this sense, when they mean accidental, it means simply that. So this one is still accidental, but you did it by on purpose. See? So it's still accidental.
But it's not. But it's not because the point is that I was asking.
Let's say that you didn't know. You just picked that one gauge symmetry and you didn't care what would be the remnant symmetry.
I see.
You just do it. And I'm reading your paper saying, look, wow, Jacinto didn't realize, but there's a remnant symmetry.
No, but it's not an
accidental symmetry.
No, it's an incident symmetry. An incident symmetry, because, for example, I just label it now. But okay, I think that because accidental symmetries, they will have the problem, for example, of electronic.
I know the term. I'm just saying this word accidental
Comes from, okay.
It's just meaning that you did not do it on purpose. Yeah. That's all. Okay. has nothing to do with being problematic or not.
Yes.
Being problematic or not, it is if it's a global symmetry. Whether it's accidental or you did it on purpose, doesn't matter. If you have an accidental symmetry, then you have a problem. Well, if it came from a gauge symmetry, then there's no problem. Okay? There's no problem. It came from a gauge symmetry. Whether it was accidental or not, irrelevant. If it came from a gauge symmetry, it's fine.
The point is that battle, he will argue that if I have an accidental symmetry, discrete symmetry, it won't be conserved. That's exactly what I wrote in here.
Actually, the last sentence you wrote in the
Exactly.
above.
Exactly here. So that's exactly the difference.
I know, but look, go up. Go up. Up. The first slide. Here, then, okay. Go back. Go down. Here. There. That's the problem. Global discrete symmetries are violated by quantum gravitational effects.
Yes.
So this is not easy at all.
Yes.
So this has to do with the Hare theorem. Teorema do cabelo. Hare theorem, which says that at the Planck scale, where expect that gravity is quantized, then black holes do not conserve global charges. So it's like if you have a global charge, then at the global charge, that symmetry happens at the horizon of the black hole. And let's say you have a symmetry near the horizon of the black hole. If it is continuous, if it's a global symmetry, and then the black hole eats that global symmetry, and then you can't see it from outside the horizon. So it was eaten, you violated the charge. But for gauge symmetry, that won't happen. What? I don't know why is that, but that's the argument. That's the Hare theorem. It's a theorem. Nobody proves. It's a theorem. Okay. So this is not true. I mean, it's not a solid statement, because the same thing happens for an axion. The Pechenkin symmetry is still a global symmetry. Will have the same problem, and people don't care. So this is not you cannot be guided by first principles using this argument saying, if it's an accidental symmetry, then it's not violated, it's problematic, so I won't do it. No, that's not solid. Okay? It's just okay if you write a paper about it and then you use it in your favor, but it's not solid.
Mm-hmm.
See?
I see. Okay, so I'll try to be more. Okay, I will just follow my notes because I think it will be faster. But okay, so basically in the paper he will define the difference between these accidental gauge symmetries, global symmetries, and the discrete gauge symmetries. Basically, the discrete gauge symmetries comes from the gauge symmetries after breaking. So in the case of accidental global symmetry, it doesn't happen. Basically, it's that, but that's okay. So it's an example that I discussed with Fernando. And for the case of accidental global symmetries, we could think, for example, about the lepton number that is conserved in the Stoner model, but it doesn't have an explanation for that. It just happened after all. After we do everything, it is conserved. But then when we use, for example, a kind of non-renormalizable theory, it happens that it doesn't conserve it. It doesn't happen, for example, for the case of discrete gauge symmetry. That's the argument. And I accepted it because I can't I can say no, and then I would have to send an email explain why. So I have to accept. But that's okay. So let's take some examples. Okay, let's take. The idea is I have a gauge. I want to explain why I could have dark matter in my model without put it by hand. So I must have a symmetry, and this symmetry must be a kind of Zn symmetry. Usually, if I have just one component, dark matter, it will be a Z2, and it means a reflection. It means that I will make this kind of thing here. I will have my chi. This chi goes to minus chi, and then it will prohibit some terms in my Lagrangian, blah, blah. But I won't say that it comes from a gauge symmetry, a gauge principle. It comes from an interaction, fundamental interaction in nature. So I have an explanation for that, but I want to go beyond it. I just don't want one component of dark matter in the universe, but I want more. And how I could do that? Basically, that's what this paper does. So he takes the first example of a Z2 symmetry. In the case of Z2, we're gonna have, he takes this Lagrangian here, and the Lagrangian will give where here we have this UD symmetry, U1D symmetry. What the hell? What's that? But this scalar will be a dark Higgs. It means that it will broken this U1 symmetry, and it has 2. The sign assignment is 2, and this is a matter field, a scalar matter field, which has charge 1. So in this case, some very specific things will happen here, but anyways, at the end of the day, we're gonna have just this only, we're gonna have, that's because the guys here, sometimes I may confuse what I have to say because of the undergrad guys. But anyway, so usually if we have a field, a scalar field, we can parameterize this field, expanding it in terms of 2 real fields in this kind of, because if we assume that it is complex, then we're gonna have the imaginary and the real part. It's important for main proposal, but for now, basically what will happen is I can ensure that there will be a dark matter particle, as I said, that will be stabilized, okay, by this symmetry. And in this case, since I have 2 fields, which is real fields, the S and P that comes from this chi1, I have to assure that the mass of one of them is larger than the other to avoid decay of one of to avoid decay of this field into the other. This equation basically means that P could decay into S, but S cannot decay in nothing, right? So S is the stable one; it doesn't decay. So then he talks a little bit about diagonal interactions that will be very important in the direct detection searches, and the implications basically will be this kind of inelastic scatterings, and it's a very complex thing that I don't have knowledge on that, just a little bit. And at the end of the day, it also. Yes, I hope so. Thank you, Sensei. But anyway, we also would have collider implications, and it will happen because this P guy, which is heavier than the S guy, which is dark matter, this P guy could decay into S and that same particles via interactions via other portals. For example, I could have a Z guy. I could have also the interaction between these dark Higgs with the Higgs of the Stoner model, and this guy could anyway at the end of the day decays into the visible. Then I could maybe see this guy in my I could probe these particles in my colliders. So sometimes, maybe, hopefully, we may detect, for example, a new particle that maybe isn't dark matter, but it will give us some hints about dark matter because it comes from the dark sector, for example. If it's a new interaction, if you discover a new interaction, for example, and it doesn't mean necessarily that it must be a gauge interaction, it could be a UCAL, a kind of UCAL interaction. So it's a very, very interesting and very exciting things. Okay, so beside the scalar, we could have also just one component dark matter model in the where our dark matter candidate is a fermion. In this case, we would have different terms because the mass term of the fermion is a little bit different. It's necessary to have a kind of a chiral chiral component, etc. Then we can build it. It comes from direct Lagrangian. But anyway, we would have the same idea. The idea remains the same. One of the guys will have a small mass, and at the end of the day, this guy would be the dark matter particle, blah, blah, blah. It's indeed, in this case, he just make things complex. We can have simple models for dark matter being a fermion. That's okay. But we can also have, instead of a Z2 symmetry, we could have a Z3 symmetry. Usually, this kind of symmetries don't apply to fermions. Usually, in the literature, we're gonna find just for scalars, because it will prevent some terms in the potential, for example, and then it will stabilize a dark matter candidate. So in this case, for example, that's the one that I talked, that we can have this kind of semi-annihilation process. There is a paper from Carlos Iaguna that was visiting our group, where he talks a little about semi-annihilation processes in a two-component dark matter scenario.
Okay, I think we should stop there.
Yes, I will stop now. Just talk a little. Just talk about
Now
this.
do you know why?
No, that's a question that I have. I think it comes from the amplitude. Exactly, but I didn't do the calculation, so it's
So
like
I
have to
have
do.
to be chi, right? Always.
Yes.
So let's say scalar is a fermion, whatever. I need a chi here. Direct detection requires a dark matter initial state and then quark in the initial state. Now tell me how you can start a chi here, but you need two other chi's there. So you need a quark and you need a quark. You have one option only left. How the hell are you gonna scatter this guy? This guy, you need two more.
Via the chi.
Okay, so chi comes.
And then chi here. Chi would interact with the.
But that's the only two. And this guy with this guy, yes. Then you have a fermion, direct with fermion, that violates Lorentz. Right.
That loop diagram.
And if you do it, we said at 3 level. 3 level, how much you can't do this. But it's a fermion, won't matter. You can't do this. You cannot have a fermion going fermion.
But in this case, it's a scalar.
Okay.
No, I mean, okay, so it's possible.
Yes.
So that's would be the.
But now, wait. Now, let's go back a bit. So in terms of diagrams, it's possible, right? Now you have a vertex which is chi or quark. Means that chi decays into quark.
Yes.
So it's no longer stable. But then you have U quarks. So chi has to be lighted in the U quark mass for this scattering to be.
But I could, for example, put some kind of bounds on the decay rate. I mean, on the timeline.
I know, but the bound you have to place on the lifetime of this, you just be no scattering at all.
Yes.
For this guy to be stable in light, because if you remember, when you compute the scattering rate, the scattering rate is the lifetime proportional to the mass of the mother particle, either squared or the third power, depends on what the nature is, a fermion, vector, or scalar, but it's always proportional to the mass. So if you make it very light, means that the lifetime will be small, and then it's excluded. So if you move it to be light, the lifetime is too small, you exclude it. But you want it to be light for this scattering to take place. But then it won't matter, because this coupling has to be very, very small. This coupling between this, very, very small for the lifetime to be large, right? So it's not proportional to some lambda. We make lambda very, very, very tiny. For this lambda to be tiny, this is lambda at the same power. Make lambda to be very small for the lifetime to be large, but then if lambda is small, then because the scattering rate is proportional to lambda, and lifetime is 1 over gamma. That's why this gamma appears in the denominator.
I could also, for example, see a problem because the interaction would be even smaller. Even if I don't think about it, but about just the scattering, I would have my amplitude, this kind of, for example, G pi interaction, and here would be another kind of interaction, right? I mean,
I know, but it's no longer scattering force.
It would be, yes, exactly. But it could be, no? Could be something like.
So you're saying that an atom will transform
like
into a new element?
But it could do something like that.
Like what is that one there?
Sorry.
I.
Three. Two.
You violate
Probably
energy.
there will be.
So you're violating energy.
Where?
Well, this guy's at rest,
Yes.
right? So what is the energy of this guy? Let's say the
The
mass.
mass.
And what is the total energy here?
Yes. Yeah.
You're violating energy.
So we have a problem. As they say, we have a problem. The conclusion is, indeed, we have a problem. We want to avoid this kind of terms.
Can I add something?
Please.
It's interesting that the early universe production of the relevant is driven by semi-annihilation instead of annihilation. You can allow those annihilations to be stronger without mess up the relative abundance measured by Planck.
However,
However, what?
however, you still have to obey the CMB bound
The CMB bound?
on the annihilation process. Which has nothing to do with has nothing to do with right this.
Okay.
In this case,
It's like indirect detection, for instance. There is a bound on sigma v, right?
Right.
It has nothing to do with right this or dark matter.
But
This sigma v has to be obeyed regardless. And that bound is around T minus 26
so it's in the ballpark of the
thermal relative. So even if you have a cross section that would a thermal relative be very small, let's say the canonical scenario we have this, right? Right? That's what we have.
That's right.
And if you know, for example, I can do an simulation to be very strong, very large, and that this simulation, no longer this one, drives the relative density. So okay, fine. It's not true. However, this bound is there no matter what.
I'm not familiar with that bound, so
That bound on sigma v is the
indirect detection.
for indirect detection.
right.
So it says that so everything above is excluded. So it's saying the flux of gamma rays you can observe is proportional to the annihilation cross section over the mass in the second column.
It starts to be something more.
So I haven't seen any gamma rays coming from dark matter annihilation. Therefore, I can place a bound on this ratio, which is this one right there.
Yes.
Has nothing to do with right this.
Yes, yes, yes.
Yeah,
But
okay.
you mentioned CMB.
There is also one for CMB, because if dark matter annihilated at early times would induce E plus E minus very large amount of E plus E minus. And that E plus E minus will scatter off photons of the CMB and change the Poisson spectrum of the CMB. And that's a very strong bound and the bound for C and D is around 10 to minus 20, a bit weaker, stronger than this. So let's say this is like 3, it would be like 1 with minus 27. So C and D comes around here. So no matter what you can come up with that will change the radical density, but the bound on sigma V, which is nothing to do with radical density, you have to obey. So, okay, fine, you have a different model to explain a different annihilation mode to explain the radical density, but the indirect detection bound will still be there. So what? The reason why you said this, because in the papers they justified it in a different way. If semi-annihilation drives the radical density, then you can, usually when that happens, is because the direct detection bounds are weak. So you can make direct detection to be really, really weak. It's a way to disentangle annihilation from direct detection. And that's good because usually the bounds from direct detection are usually the most restrictive. So semi-annihilation is a way to just separate annihilation relative density from direct detection. That's all. But the bounds you still have to obey.
So what I was saying is that if you have semi-annihilation driven relevant production, you can allow the annihilation to be somewhat stronger and to put stronger bounds on the model in view of indirect detection. So you are hiding one signal, but raising up others. So
yeah, but the point is, semi-annihilation drives the radical density, so it's large. Okay?
Yes.
Fine. So let's do it the following. Omega H squared is 326 over sigma V for annihilation. Okay? Let's put it like this. Sigma V for co-annihilation.
Finish here.
Let's
Because
assume
the discussion
okay?
is on the board.
Then you say for co-annihilation is larger. Right?
Bye-bye.
Then we're going to drop it first. This one is larger. So annihilation is very small. Annihilation means